For decades, we thought we understood the universe. The Standard Model, the most successful theory in human history, explained 5% of everything we knew. We thought the puzzle was complete, but we were wrong. Horribly wrong, because the experiments at CERN found something the model could not explain. The signals were unsettling. An internal report described the signal as inconsistent with single timeline causal propagation, something physics was never supposed to allow. And yet, the signal lasted for a full 100 nanoseconds, making it impossible to ignore. But that wasn't the most disturbing part. These anomalies reappeared again and again in 3% of all events, something that should never happen if there is only one reality. If your sense of reality has been shaken, but this mystery excites you, then like this video and subscribe, because what you're about to see will rewrite the physics books. Are you ready? Here we go. There is a machine buried deep underground. It does something human technology has never achieved before. It smashes particles together at speeds so close to the speed of light that the energy released echoes the first moments after the Big Bang. Because this isn't just a particle accelerator, it is the most complex scientific instrument humanity has ever built. We're talking about a tunnel with a circumference of 27 kilometers, stretching beneath the border of France and Switzerland. But most people don't know what's inside. Thousands of superconducting magnets line the inner walls of this giant ring. That is why these magnets are cooled to temperatures colder than outer space, around -271.3 degrees Celsius. These conditions are necessary to steer beams of protons around that massive loop at 99.999% the speed of light. That's more than 11,000 laps a second. Because when those beams collide, the energy released at the point of impact momentarily recreates the conditions that existed less than a billionth of a second after the universe began. This is not a metaphor, it is a measured fact. That is why we can call this machine not just an accelerator, but also a time machine. But when this machine was first turned on, something went wrong. Almost instantly. It happened in September 2008. A faulty electrical connection between two magnets caused a chain reaction. Liquid helium leaked into the tunnel. A total of 14 magnets were damaged. The machine was shut down for over a year. Some called it a bad omen. Most called it an engineering problem. But a small number of researchers quietly noted something stranger. The failure did not match the expected error model. This connection had been tested repeatedly. The system had been verified because it failed in a way the models did not predict. Even the failure mode itself was an anomaly. This detail was not widely reported at the time because the main focus was on getting the machine running again. When the accelerator came back online in 2010, it was run at lower energies than originally designed as a precaution. But the data began to flow. In the first few years of operation, fascinating results arrived. Groundbreaking discoveries were made. But sometimes, deeply confusing findings also emerged. Most of these puzzles were solved. Physicists are good at solving puzzles, but a few were not. They were noted, archived, and the teams moved on without a second look. The turning point of this story came on July 4th, 2012. The world celebrated when CERN announced the discovery of the Higgs boson, because this was the final missing piece that completed the standard model of particle physics. It was the last link in a puzzle that had been assembled for decades. But when the puzzle was finished, it was noticed that the number confirming the discovery didn't quite fit the next step. The measured mass of the Higgs boson was approximately 125 giga-electron volts. This number was important for more than just confirming the particle's existence, because it sat at a very specific point on a theoretical spectrum. It was high enough to suggest that the universe was stable, but it was also low enough to suggest that it might not be permanent. Physicists describe this situation with the term metastability. It means the universe exists in a kind of false stability, like a ball resting in a shallow dip on a hilltop, stable for now, but vulnerable to the right nudge at the right time. In theory, this nudge could come from a quantum fluctuation. It could appear anywhere in the universe, at any time, without any warning. But that's not what kept the researchers awake at night. The truly strange thing was a secondary measurement taken in the same dataset that confirmed the Higgs. One of the detector arrays, the compact muon solenoid, recorded a short, anomalous signal during the discovery window. The signal lasted for about 4 beam crossings. A beam crossing in the Large Hadron Collider lasts 25 nanoseconds. Therefore, the signal existed for roughly 100 nanoseconds in total. In particle physics, 100 nanoseconds is long enough to be significant. The signal did not match any known particle. Moreover, it did not match any theoretical particle in the literature. Its energy profile was described internally as inconsistent with single timeline causal propagation. This phrase appeared in a draft of a paper, but it was not in the final published version. The researchers who wrote that phrase were asked to revise the language before submission. The revision replaced the phrase with a reference to background noise from beam halo effects, a standard boilerplate explanation for anomalous signals near the detector threshold. Most of the original authors signed the revised paper, but one did not. That researcher left the collaboration the following year. The reason was listed as personal. They have not published on particle physics since. This brings us to the Standard Model itself. This theory is the most tested scientific theory in human history. Its predictions have been confirmed to extraordinary precision. In some cases, it matches experimental results to more than 10 decimal places. In short, it describes everything we see, touch, and measure. But, despite being one of science's greatest achievements, there are things it fundamentally cannot explain. The Standard Model has no explanation for gravity on the quantum scale. It offers no mechanism for the matter-antimatter dominance we observe in the universe. Because, according to the theory, equal amounts of matter and antimatter should have been created in the Big Bang. If that had happened, they would have annihilated each other, leaving only radiation behind. But we are here. Therefore, something broke that symmetry. The Standard Model cannot explain how. More importantly, it cannot account for dark matter, which appears to make up roughly 27% of all mass and energy in existence. Nor can it explain dark energy, which is understood to be driving the accelerated expansion of the universe. These two make up about 95% of the universe. Therefore, the Standard Model, the most successful theory of human science, actually provides a framework that describes only about 5% of everything that exists. Everything else is labeled with one word: dark. Dark means we have no idea what it is. Therefore, many researchers at CERN were actively looking for evidence of physics beyond the Standard Model in every major dataset. The collider was not built just to confirm what we know. Its main purpose was to find what we do not know. In some datasets, there were hints, data appearing at unexpected energy levels, showing tantalizing deviations from predicted values. Some grew stronger and became real discoveries. Others faded away. But a few remained exactly where they were, stable but inexplicable, too strong to be dismissed as noise, yet too strange to be comfortably placed in any known category. Because in 2015, as the collider reached its highest energies yet, something appeared in what physicists call the diphoton channel. And this thing, 2 photons produced at an energy far above the Higgs mass, could not be produced by any known particle. The signal briefly reached statistical significance, because this could have been the first concrete evidence of a new particle, new physics, beyond the Standard Model. The particle physics community was in a quiet frenzy. Hundreds of papers were written across the field, all speculating on what this signal could represent. But, as more data was collected, the signal slowly faded. It was eventually declared a statistical fluctuation. The file was closed. Everyone moved on. But one theoretical paper published before the signal disappeared modeled it differently. The authors suggested that the signal was consistent with a resonance pattern of 2 overlapping quantum states from different vacuum configurations. In simpler terms, this signal could only be explained if 2 slightly different versions of quantum reality were contributing to the same measurement at the same time. This paper was published. It received limited interest because the signal it described was gone. So, the theory fell silent. But the math behind that paper did not disappear, because what was about to emerge in the second dataset would make that math very relevant very soon. This story is not just about particles, it is also about memory. Most people know the Mandela Effect as an internet curiosity. It's when large groups of people share the same false memory. The Monopoly man with a monocle he never had. A movie called Shazam starring a comedian who never made it. The spelling of a beloved children's book series that turns out not to be the official spelling used by the publisher. These shared false memories began to circulate widely on the internet around 2010. They are named after the widespread false belief that Nelson Mandela died in prison in the 1980s, decades before his actual death in 2013. The popular explanation is quite simple. Human memory is not like a recorded video, but a reconstructive process. We fill in the gaps, we borrow details from similar memories, and we update our memories without realizing we are doing it. A false memory shared widely enough is reinforced in other people's minds through suggestion and social confirmation. This is a well-documented phenomenon in psychology research, because it is almost certainly the dominant explanation for most examples of this phenomenon. But there is a minority view, and some of the people who hold this view are not conspiracy theorists or internet personalities. They are credentialed physicists who have spent their careers working with the mathematics of quantum reality. This minority view argues that some instances of shared false memories could represent actual discontinuities in lived reality. Not because people are physically traveling between timelines, like characters in a movie, because, on a quantum level, the boundary between possible states is not always as hard and clear as classical physics assumes. Under certain interpretations of quantum mechanics, particularly the many worlds interpretation and its related decoherence frameworks, the universe is constantly branching into diverging branches. Most branches are completely separate, but near certain high-energy events or extremes of quantum coherence, the possibility of informational leakage between adjacent branches is mathematically non-zero. This probability is very small, but there is a meaningful difference between very small and exactly zero. Therefore, a small number of researchers, not under official CERN sanction and working off the record, began to map the timing of widely reported Mandela Effect instances against CERN operational data. High-energy run dates, beam collision events, peak luminosity periods. What they found was described in a document that circulated among a limited group of physicists in 2017. The document was never formally submitted for publication. The few who received it described its contents as disturbing, not because the correlation was particularly strong, because it was stronger than anyone expected, stronger than chance should allow. This document was never made public, but the people who read it have spoken to each other privately, in ways that are very consistent. What they describe brings this story to a point where it becomes significantly harder to dismiss. The picture that emerges when we bring all these concepts together is this. We have mysterious signals appearing and disappearing in detectors, which the standard model cannot explain. We have false memories of uncertain origin, shared by thousands of people simultaneously. And we have a theoretical framework that could connect these two completely different seeming phenomena. This framework suggests that reality itself may not be as solid or as singular as we thought, because all these pieces revolve around one central question. Are the experiments at CERN only revealing the secrets of subatomic particles? Or are they, without our knowledge, affecting the very fabric of what we call reality? These questions are no longer just theoretical speculations, because those off-the-record researchers made a claim. They found a correlation, and that correlation, if true, requires us to question some of the most fundamental assumptions of modern physics. But this was just the beginning, because what was written in that document implied much more than just a statistical link. So what was the real evidence those initial researchers found? What exactly did the data show, and why did it cause so much concern within the institution? Because in the next part of the story, we go beyond a simple correlation. Because when we go beyond a simple correlation, a document emerges. The 2017 document, the one that was never made public. And the contents of that document were far beyond expectations. It was not just a statistical oddity, because what they found was too strong to be a coincidence. Here is the first shocking discovery. The geographical distribution of the informal correlation study made the findings difficult to dismiss. The researchers did not pull data from a single forum or a single country. They consulted archived discussions from multiple continents, multiple languages, and numerous internet communities with no documented overlap. Because the consistency of the correlation across these independent populations was what made it feel like more than noise to the physicists who first read it. These were people with positions at recognized institutions, not fringe figures. Their methodology was described by those who reviewed it informally as rigorous and carefully constructed. The data it relied on was real CERN operational data. This data was cross-referenced with public archives of reported Mandela Effect events that had high consensus rates. High consensus means that a large number of people independently reported the same specific false memory, people with no connection to each other and no common source for the claim. The correlation they found was temporal. During periods of high-energy beam collisions at the Large Hadron Collider, the rate of online reporting of high-consensus Mandela Effect events showed a measurable increase. The increase was between 12 and 18% above the baseline. This was consistent across 3 separate high-energy run periods spanning multiple years. When the researchers applied standard statistical tests, the probability of the correlation occurring by chance was calculated to be less than 3%. In most scientific fields, 3% would not pass the publication threshold, but in physics, the standard is much stricter. However, the researchers were not claiming the correlation proved anything. They were only claiming it was strong enough to warrant a formal investigation. This is the normal scientific response to a thought-provoking but inconclusive correlation. The request was made, through the proper channels, to the proper people with the authority to approve it. It was denied. The reason given was that the correlation was methodologically unsound, relying on self-reported anecdotal data that could not be independently verified or controlled. This was a fair criticism. The researchers revised their methodology proposal to address the concern. They designed a more rigorous protocol. They submitted the revised version, but it was denied again. No new justification was offered. This was one finding. But there was another, and this one was hidden in the middle of the celebrations. The 4th of July, 2012, the day the Higgs boson was discovered. But in the data recorded that day, there was something else. Something that shouldn't have been there. One of the detector arrays, the compact muon solenoid, recorded a short anomalous signal during the discovery window. It lasted for about 4 beam crossings. A beam crossing lasts 25 nanoseconds. The signal lasted for roughly 100 nanoseconds in total. That's a lifetime in particle physics, because this signal did not match any known particle, nor did it match any particle in the theoretical literature. But that wasn't the real shock. The real shock was in the initial internal description. The energy profile was described as inconsistent with single timeline causal propagation. This phrase appeared in a draft of a paper, but it was not in the final published version, because the researchers who wrote that phrase were asked to revise the language before submission. The revision replaced the phrase with a standard explanation, a reference to background noise. This is the exact opposite of how science is supposed to regulate itself. Certainty was traded for ambiguity. Most of the original authors signed the revised paper, but one did not. That researcher left the collaboration the following year. The reason was listed as personal. They have not published on particle physics since. In the context of everything surrounding this story, that sentence is one of the most carefully chosen things anyone connected to this story has ever said publicly. The decision not to investigate was not about the quality of the question. It was about the nature of the answer we might find. And now, we come to a fact from mainstream physics that rarely makes headlines but should. In 1997, a CERN experiment called CERN produced verified, published results showing that certain particles behave differently depending on the direction of time. This is not speculation. This is verified, published science, repeated and accepted by the physics community for nearly 30 years. It's called CP violation, and it is one of the most profoundly disturbing verified results in all of modern science, because it confirms that the universe has a built-in directional asymmetry at a fundamental level. It is not perfectly symmetrical between matter and antimatter, between spatial mirror images, or across the reversal of time. The universe has a preferred direction, and no one fully understands why. This relates to a concept called CPT symmetry. physicists long assumed that the laws of physics obeyed three symmetries: between particles and their antimatter counterparts, c, their mirror images, p, and the reversal of time, t. The C-Clear experiment showed that the combined C and P symmetry is broken. This was predicted by the standard model. But it also confirmed something much stranger. The universe may have evolved from conditions that are not symmetrical under time reversal. This is mainstream physics taught in graduate programs worldwide. But there are theoretical physicists who take this logic into a much more speculative and, in its implications, much more disturbing realm. What if the decoherence boundary between quantum branches is not perfectly stable during certain high-energy events? In these windows, the informational boundary between what we experience as one timeline and what exists as a parallel quantum branch could theoretically be thinner than at other times. Therefore, CERN intentionally creates these high-energy events repeatedly at the highest energies human technology has ever reached. The C-Clear result, published and confirmed in a prestigious journal almost 3 decades ago, gives this theoretical window a mathematical footing it would not otherwise have. And that footing is stronger than most people realize, because this opens the door not to coincidental anomalies, but to the inevitable consequence of a fundamental law of physics. So, what was seen when this door was opened? Because what was found turned this theoretical possibility into a disturbing reality. And this reality became even more disturbing during the second major run of the Large Hadron Collider. This period lasted from 2015 to 2018. The collider was operating at 13 tera-electron volts. This was nearly double the original design energy. It was the most powerful continuous particle collision experiment in history up to that point. The detectors were upgraded, the data rates were unprecedented, and hidden within that massive data set, in the records of the Atlas detector collaboration, was an anomaly that was never published as a standalone result or officially explained. It was discovered during a routine scan of 4 lepton events. 4 lepton events are collision outcomes where 4 leptons, meaning electrons or muons, emerge from a single collision point. These events are rare, but they are also extremely clean in terms of measurement, because leptons interact weakly with detector material, leaving precise, well-defined tracks. Of all the signals particle physicists work with, 4 lepton events are some of the most reliable. In a subset of 4 lepton events recorded during a specific high luminosity run in 2016, the invariant mass distribution showed a secondary structure, a small secondary peak sitting next to the expected Higgs signal. This peak was narrow. It appeared at an energy close to, but not identical with, the primary Higgs mass. It appeared in roughly 3% of the events in that specific subset. 3% sounds small, but in a dataset of millions of events, 3% means a number of anomalous readings too large to ignore. The immediate assumption was detector error. The data was re-examined. The detector response was simulated with high precision. The error hypothesis was tested, but could not fully explain the secondary structure. A second assumption was pileup, the contamination of individual collision events with overlapping collisions from nearby beam crossings in the bunch. Corrections were carefully applied, but the secondary structure persisted. It was slightly reduced, but still there, and still structured. At this point, 3 possible explanations remained. A new particle with a mass extremely close to, but distinct from the Higgs. A quantum interference effect from some kind of Higgs mixing. Or something else entirely. Something for which there was no established category in the analysis pipeline. The researchers chose to investigate the first 2 options. Both were dead ends. No new particle fit the profile. Higgs mixing scenarios required coupling parameters that violated known constraints from existing data. The third option was not pursued in any publicly available document. The anomaly is listed in the Validated Data Archive as an unexplained instrumental artifact. This classification was applied after the 2 mainstream explanations failed. This should not be the way science ends an investigation. But this was just the beginning, because in 2019, a theoretical physicist connected to 2 separate CERN collaborations gave a lecture at a European university. The lecture was titled something like Quantum Decoherence Extremes and Observational Artifacts. It was not a high-profile event, the audience was small. The lecture was not officially recorded in any format, But several attendees took careful notes. Parts of these notes were shared on a closed physics discussion forum. According to these notes, the lecture made 3 specific claims. First, that during high luminosity runs at the Large Hadron Collider, the instrumentation recorded signals that were inconsistent with themselves in a specific and repeatable way. The inconsistency was not random noise. It had a coherent internal structure that noise does not have. The word the speaker used was structured. Second, that when the energy profile of these structured anomalies was analyzed in detail, it showed what the speaker called dual origin characteristics. The signal appeared as if it had originated from 2 separate but overlapping quantum states simultaneously. In a single timeline universe, a detector measuring a particle collision at a specific point should see a signal with a single spatial and temporal origin. 2 simultaneous origins with a coherent separation has no standard explanation anywhere in the current theoretical literature. The third and most serious claim was that these findings were reviewed internally at the highest level, and a decision was made to reclassify them as instrumental errors, without completing the verification procedure that the collaboration's own data quality protocols explicitly require for anomalies of this significance. This meant the anomalies were not explained by the data, but categorized by an administrative decision. One person who attended the lecture later described the atmosphere in the room as extremely quiet for a very long time. But the shock waves were not limited to CERN. On another continent, a completely different experiment had found another crack in the standard model, and this took the story to a completely new level. In April 2021, the results of the muon G2 experiment at Fermilab in the United States were published. It instantly became one of the most talked about results in physics. This experiment was measuring a specific property of the muon, called its anomalous magnetic moment, with extraordinary precision. The result was a discrepancy. The measured value differed from the prediction of the standard model by a statistically significant amount. When combined with earlier data from Brookhaven National Laboratory, it reached a significance of 4.2 sigma. The standard threshold for a discovery claim in particle physics is 5 sigma. At 4.2 sigma, the muon anomaly was not technically a confirmed discovery, but it was too significant and consistent to be dismissed as a fluctuation. This was completely independent of everything at CERN: different continent, different facility, different technique. But it pointed in the same direction. The standard model was incomplete. When all these findings are put together, the picture that emerges is both astonishing and deeply unsettling. We have a correlation that cannot be explained by chance, with a specific pattern in time. We have signals appearing in the most reliable detectors, described as dual origin, that cannot be explained by standard physics. We have the archiving of these findings by administrative decision before the official verification process was complete, and we have a result from a completely independent experiment showing a 4.2 sigma discrepancy with the standard model. These are no longer isolated incidents. They are a chain of interconnected evidence. But how does this chain work? What is the physical mechanism behind these anomalies? What does it mean for a signal to come from 2 places at once? To find the answer to these questions, we must descend into the deepest and most confusing area of physics. Because if these findings are correct, a mechanism has begun to operate that requires us to reconsider our fundamental assumptions about the nature of reality. And that mechanism, which lies at the foundation of everything. But how does this mechanism work? What is the fundamental physics that ties together so many different and disturbing findings? So far, we have looked at shocking discoveries. We have moved fast. But now, we must slow down and descend into the theories that lie at the foundation of everything, under the hood of the engine. Because only when we understand these complex but fascinating mechanisms can we grasp what might have really happened at CERN. Therefore, we now go into the technical details. The first and perhaps most important concept at the heart of this problem is the quantum vacuum. In everyday language, a vacuum means empty space, nothing. But in quantum physics, the vacuum is the most active place in existence. It is a roiling sea of quantum fields, all existing simultaneously in their lowest possible energy states. Virtual particles constantly pop into and out of existence. They borrow energy from the vacuum and return it almost instantly. This happens so fast that they cannot be directly observed. But their effects are absolutely measurable. The Casimir effect is a direct experimental consequence of vacuum energy. Two uncharged metal plates placed very close together experience a small but measurable attractive force. This force arises from the difference in vacuum fluctuations between the narrow space between the plates and the open space outside. This experiment has been repeated in laboratories worldwide. It is not a theory, it is a measurement. The vacuum is real, and it is active. The vacuum is also the foundation of physical reality. Every particle that exists is an excitation of one of these underlying quantum fields. The electron is an excitation of the electron field. The Higgs boson is an excitation of the Higgs field. And the Higgs field is special because its vacuum state, the value it settles to when undisturbed, determines the masses of all other fundamental particles. If you change the vacuum state of the Higgs field, you change the properties of every particle in the entire universe. If the vacuum state of the Higgs field is not the lowest possible energy state, meaning there is a lower energy state the field could theoretically fall into under the right conditions, then the universe is metastable. The measured Higgs mass of approximately 125 gigaelectron-volts places us right on the border between stable and metastable, marginally in the metastable region according to most detailed calculations. In a metastable vacuum, the boundary between our current state and the lower energy state is protected by a quantum barrier. Under normal conditions, quantum tunneling through this barrier is exceptionally unlikely. The timescale for spontaneous vacuum decay is estimated to be much longer than the current age of the universe. But what happens during an event that momentarily recreates the extreme early universe energy densities in a confined space? Right at the edge of this barrier, by creating these conditions, the collider is in fact pushing against this very barrier. Therefore, the vacuum itself is the first and most fundamental mechanism of our story, a universe built on a fragile foundation. The second mechanism built on this fragile foundation comes from a young physicist named Hugh Everett, who presented his PhD thesis at Princeton University in 1957. His thesis proposed a radical reinterpretation of quantum mechanics. According to the standard Copenhagen interpretation, a quantum system exists in a superposition until it is observed, at which point it collapses into a single definite state. But Everett proposed that no collapse ever occurs. Instead, every possible outcome of every quantum event actually happens. The universe splits, each branch is real, each branch continues to evolve independently forever, with no interaction between the branches. This is the many worlds interpretation. His thesis was poorly received. His advisor, John Wheeler, spent months trying to get Everett to tone down the implications of the results. But Everett largely refused. His thesis was accepted and published in a shortened, diluted form. Everett left physics shortly after and went into defense research, and he never published on quantum mechanics again. But his idea did not die with him. The key concept of modern many worlds thinking is decoherence. This is why we do not experience quantum superpositions in everyday life. The reason a table is not in multiple places at once is that large objects continuously interact with their environment. These interactions rapidly destroy quantum coherence. Decoherence is the process by which quantum superpositions effectively become classical for all practical purposes. The branches do not disappear. They become causally disconnected. They cannot affect each other, normally, and it is this word, normally, that is doing a great deal of work in our story. Because some theoretical frameworks built on Everett's foundations allow for a very specific exception. At sufficiently extreme energy densities, of the kind produced in the Large Hadron Collider during high luminosity runs, the decoherence suppression that normally keeps quantum branches causally separate can be theoretically stressed. Not broken, but stressed. This stress may be enough to allow for a small but non-zero informational leakage between branches that are still very close to each other in the space of possible quantum states. This is a minority position in theoretical physics, but it is defended by credentialed physicists, published in theoretical journals, and provides a coherent framework for interpreting the anomalous signals at CERN. The question of what this leakage would look like in detector data brings us directly back to dual origin signals. But a completely different theoretical framework trying to solve the problem of matter-antimatter asymmetry arrives at the same conclusion. This brings us to our third mechanism, the CPT symmetric universe, or mirror universe model. As we know, equal amounts of matter and antimatter should have been created in the Big Bang. If this symmetry were perfectly preserved, they would have annihilated each other, leaving only radiation. But we are here. Therefore, something broke this symmetry. The CP violation we measure with experiments like the 1997 CPLEAR experiment is real. But the amount of CP violation measured in the standard model is orders of magnitude below what is needed to explain the imbalance we observe in the universe. This gap is called the baryogenesis problem. One theoretical solution to this problem involves the existence of a second, antimatter-dominant universe evolving in an opposite temporal direction. In this model, our universe and its antimatter counterpart were created simultaneously at the Big Bang. They branched from a single symmetric starting point. One branch became matter-dominant, the other antimatter-dominant. Each branch would experience time as flowing forward from that starting point, and each would be, under normal conditions, causally separate, invisible, and inaccessible to the other. This is not a fringe idea invented to explain mysterious internet phenomena. Versions of it have been published by credentialed researchers in reputable physics journals. The model makes specific, testable predictions about neutrino properties that are actively being tested in experiments worldwide. But it also makes a structural prediction that connects directly to CERN. If a CPT symmetric partner universe exists and is causally adjacent to ours at the level of the quantum vacuum, then extreme energy events that stress the vacuum decoherence boundary will be the most likely events to produce detectable artifacts from the partner universe. These artifacts would appear in detectors as structured anomalies with dual origin characteristics, carrying information from a universe where the parameters of the standard model are slightly different from our own. This is exactly how the CERN anomalies were described by the researchers who studied them. Exactly. Two completely independent paths lead us to the same disturbing conclusion, a signal that appears to come from two places in the detector at once. But there is one more mechanism that makes this puzzle even more complex, because alongside these two physical explanations, there is another, equally disturbing possibility coming from a completely different field. And this possibility questions our most fundamental assumptions about the nature of reality. And this possibility comes not from the depths of physics, but from the intersection of philosophy and computer science. This is our fourth mechanism, the simulation hypothesis. This idea argues that if technologically advanced civilizations tend to run simulations of their ancestors, then the number of simulated realities will vastly outnumber the number of real base realities. Therefore, statistically, our odds of living in a simulation are much higher than our odds of living in a base reality. This is not just a late-night chat topic. It is an argument that has been taken seriously by serious scientists and mathematicians, because its connection to the CERN question is subtle but direct, and it arises from a very specific prediction. In a simulated reality, the question of timelines takes on a completely different character. The intersection of two timelines is not a property of a physical universe, but a property of a computational system. In a simulation, timeline splits would be implemented as branching data structures, separate computational threads running in parallel. Timeline mergers or informational leakage between timelines would be implemented as data reconciliation events. That is, moments where overlapping computational states produce interference patterns in the output. Anomalous signals at high-energy collision points would emerge, where the computational substrate of the simulation is being stressed in ways it was not designed for, or where the processing for the collision region is pulling data from multiple cached computational states at once. Because the local energy density exceeds the parameters, the simulation is optimized to handle cleanly. This is obviously speculative, but it provides a second, completely independent framework that predicts the exact kind of anomalous signal described by the CERN researchers. A structured anomaly that looks like two overlapping states instead of a single state. An anomaly that does not fit into any category defined by the physics of a single reality. A signal with dual origin. Characteristics. Different assumptions, different math, different metaphysics, but the same predicted observational signature. This is a phenomenon that science calls convergence. The fact that two completely different theoretical frameworks, the many worlds wave echo hypothesis and the simulation substrate stress hypothesis, both produce the same prediction for what CERN would see if either of them were true, and what CERN reportedly saw matches both predictions. Matching a prediction is not the same as confirming a theory. Alternative explanations must be rigorously ruled out first, but the convergence between two independent frameworks is something that science takes seriously as a starting point. The fact that a formal investigation was not launched despite this convergence and the anomalous data is a fact that itself requires an explanation. Moreover, the simulation framework makes a specific prediction that the many worlds framework does not, on its own, clearly make. In a simulation, the structured anomalies would not be randomly distributed across the detector. They would cluster in patterns that reflect the computational geometry of the underlying substrate. They would appear preferentially at collision energies that correspond to processing thresholds in the simulation architecture. If the archived anomalies show this kind of non-random clustering, it would distinguish the simulation hypothesis from the purely physical wave echo hypothesis. This analysis has not been done, because the data required to perform it is not public. But there is one more theory trying to solve one of the greatest riddles in physics, and it too points to the same conclusion: quantum gravity. This is a long sought-after theory that aims to unify quantum mechanics with Einstein's theory of general relativity. Quantum mechanics governs the very small, while general relativity governs the very large. But the two are incompatible with each other in a fundamental mathematical sense. One class of quantum gravity, loop quantum gravity, LQG, treats space itself as fundamentally quantized. In this view, space is not continuous and smooth at the smallest scales. At the Planck scale, a scale about 100 billion times smaller than the diameter of a proton, it is made of discrete chunks. These chunks are interconnected in a network structure that determines the geometry we experience as smooth spacetime. Just as the image on a computer screen looks smooth, but on closer inspection is made of millions of discrete pixels. In this theoretical framework, the concept of separate quantum branches becomes more concrete and specific than in ordinary quantum mechanics. Branches are not just abstract mathematical possibilities, they are different configurations of the underlying discrete spatial network. In some formulations of LQG, high-energy events can temporarily excite modes corresponding to adjacent configurations of the spatial network. These adjacent configurations would be, in the language we have been using throughout this story, adjacent quantum branches. The excitation would appear in detectors as structured anomalies with two simultaneous spatial origins. The magnitude of the effect would be small, but it would be consistent with the scale of the perturbations observed and archived at CERN. This is also speculative, but it represents another completely independent theoretical framework that predicts the exact class of anomaly that CERN reportedly observed and quietly reclassified. Many worlds wave echoes, CPT symmetric mirror universe, simulation substrate stress, and loop quantum gravity spatial excitations. 4 different frameworks, 4 different starting points, but they all point to the same place. When we understand these mechanisms, we begin to see why the institutional response at CERN is both so incomprehensible and so human. On the one hand, there is the obligation to publish and share, the foundation of scientific progress. But, on the other hand, there is the weight of the potential consequences of the findings. If any of these mechanisms are correct, then the machine is not just advancing a particle physics program, it is having an effect on the structure of physical reality itself, in a way that was never intended, never modeled, and for which no one's consent was ever obtained. In the face of this dilemma, deferring the investigation, reclassifying the data, and not looking more closely can seem like a kind of self-preservation reflex. If you don't officially prove the effect is real, you don't have to decide what to do about it. This is a logic that cannot be justified by scientific ethics, but it is entirely understandable in terms of human psychology and institutional behavior, and this is what transforms the story from a simple conspiracy theory into something much more complex and disturbing. So we have 4 different but converging theoretical paths: the fragility of the quantum vacuum, the leaking branches of the many worlds, the echoes of the mirror universe, and the glitches in a simulation or quantized space itself. Each one, taken alone, might seem speculative, But when taken together, they act like witnesses telling the same story in different languages. They all offer a mechanism to explain why we see dual origin or structured anomalies in the detectors. But, so far, we have only talked about theory and circumstantial evidence. The real excitement is when these theories meet the actual data from the latest and most powerful run of the collider. Because, in this period known as Run 3, these theoretical whispers may have turned into an undeniable scream in the data. And what that scream sounds like could change everything. And it did. Because those theoretical whispers turned into an undeniable scream in the data of the second and third runs. That scream was not just a few anomalous signals. It was a series of discoveries, each more disturbing than the last, each shaking the foundations of standard physics even more deeply. So far, we have only followed the clues, but now we reach the climax. Hold your breath, because now we descend into those shocking findings, locked away in CERN's archives, the ones that have never been fully and officially explained. And the first shock was where the data was most reliable, inside the 4 lepton events. These events are the gold standard of particle physics. They are extremely clean. They are rare. And so, when they show an anomaly, everyone pays attention. During the second major run from 2015 to 2018, the collider was operating at a then record energy of 13 tera-electron volts. And in the records of the Atlas detector, something appeared. A peak. A secondary peak that should not have been there. It sat right next to the expected Higgs signal. But it was different. This appeared in about 3% of the events in that specific dataset. Do not let that number fool you. 3% is a huge number. In millions of collisions, this meant tens of thousands of anomalous readings. This could not be an error, because the researchers tried everything. They tested the detector error hypothesis, but it could not explain the anomaly. They accounted for signal contamination called pileup, but the anomaly persisted. They looked to see if it could be a new particle, but no theoretical particle fit the profile. They tried Higgs mixing scenarios, but they violated known laws of physics. Both mainstream explanations failed. Only one option remained, something else entirely. What science is supposed to do at this point is investigate that third option to the end. But that was not done. Something else? Instead, those tens of thousands of anomalous events were stamped with a single label in the validated data archive: unexplained instrumental artifact. This is not a classification that advances an investigation. It is a classification that ends one. This was not a scientific conclusion. This was a moment where the most basic method of science was abandoned. It was an administrative decision. Someone had decided not to look deeper, and no one was explaining why. But someone did speak. In 2019, at a European university, in a non-high-profile event, a theoretical physicist gave a lecture. The lecture was not officially recorded, but notes were taken, and those notes created an earthquake in closed physics forums, because that physicist was saying the things no one dared to say publicly. They made 3 shocking claims. First, the anomalies were not random noise. They had a coherent internal structure. The word the speaker used was structured. This meant they were much more than a random error. Second, and most incredible, when these structured anomalies were analysed, they showed dual origin characteristics. The signal appeared as if it had originated from 2 separate but overlapping quantum states simultaneously. In a single timeline, this is impossible. A collision happens at a single point. It has a single origin. But these signals had 2. This made no sense in the language of a single reality physics. And the third claim was evidence of institutional betrayal. These findings had been reviewed internally at the highest level, and a decision was made. The decision was to reclassify them as instrumental error. But this decision was made before the verification process required by the collaboration's own protocols was completed. One attendee described the atmosphere in the room after the lecture as extremely quiet for a very long time, because everyone understood. This was not a cover-up of an error. This was the sweeping under the rug of a truth that could not be understood. That physicist never repeated these claims. There is no record of that lecture in the university's archives. It's as if it never happened. And then the evidence became even more concrete. so concrete that they could no longer label it an instrumental artifact and ignore it. In the third major run, Run 3, which began in 2022 and pushed the collider to a new record energy of 13.6 tera-electron-volts, the Atlas collaboration was forced to add a new data quality category to its analysis pipeline. This was a first in its history. This is not an ordinary administrative step. In a structure involving thousands of scientists, creating a new category is an official admission that the existing categories are inadequate. It is an admission that the problem is real, recurring, and now too big to ignore. And the name of that new category said it all: structured background of indeterminate origin. They were no longer calling it error. They were no longer calling it artifact. They were calling it structured. They were calling it of indeterminate origin. This was the language of the leaked 2019 lecture entering official CERN documentation. It was the institutional echo of the phrase dual origin characteristics that had silenced the room. The existence of this category is public, but what is in it is not. How many events are assigned to this category? What their energy profiles look like? Whether they cluster at specific collision energies? This information is secret. An independent researcher made a formal request to access this information. The request was accepted, but it was never fulfilled. The official response given: data under active analysis. This response was received in early 2023. Not a single publication on this topic has been released since. This was a clear violation of the principle of scientific transparency. The data was there, but it was under lock and key. And now, we come to the climax of the whole story, the most disturbing and most urgent truth. Right now, as we speak these words, in those tunnels beneath the France-Switzerland border, an even more powerful machine is being built. Its name, the High Luminosity Large Hadron Collider, HLLHC. This is an upgrade. But this is not an upgrade like changing a car's engine. This is an upgrade like taking a propeller plane and replacing it with a rocket engine. It is scheduled to become operational in the late 2020s, and what it will do boggles the mind. It will increase the rate of particle collisions by a factor of 5 to 7 compared to the current capacity. Over its planned operational lifetime, it will produce about 10 times the total collision data of the current machine. This will be the largest data explosion in history. For conventional physics, this is a dream come true. But, in terms of our story, it could be the beginning of a nightmare, because this means higher local energy densities. This means the decoherence boundary will be stressed more frequently and more intensely. If the anomalies observed in Run 2 and Run 3 are produced by these high-energy events, the high-luminosity machine will produce these events continuously, at 5 to 7 times the current rate. The structured background of indeterminate origin category will explode. They will no longer be able to ignore it as an exception. It will become the rule. And the most frightening part, if that informal temporal correlation between CERN operational periods and Mandela Effect reporting patterns is real and scales with luminosity, the high luminosity era will produce measurable, statistically significant increases in the rate of shared false memory emergence across the human population during operational periods. This is a testable, falsifiable, concrete prediction, but no study has been planned to test this prediction. Worse, there is no stated protocol for what to do if this scenario comes to pass. Complete institutional silence. They are building the most powerful reality-bending machine in history, without knowing the consequences, and nobody is hitting the brakes. Unexplained signals, leaked lectures and silent scientists, a new data category created to admit the truth, and now, a more powerful machine being built without knowing the consequences, which will multiply everything by orders of magnitude. These are no longer conspiracy theories. These are documented institutional facts. This chain of evidence points to one disturbing conclusion. CERN may not just be discovering subatomic particles, but what does it all mean? Why is such a huge risk being taken? And what exactly is this machine doing to the fabric of reality? Because CERN may have done much more than discover something. Unknowingly, slowly, for over a decade, it may have been doing something else. Because CERN, unknowingly, slowly, for over a decade, was unleashing something else. A possibility, a theoretical possibility hidden in the strangest corners of quantum mechanics that no one took seriously. And that possibility was no longer a possibility. It had become an undeniable reality, etched into the data. And the first to pay the price for this truth were the first to see it. Because one of the darkest and most epic moments in this story did not happen in the data, but in the people. The researchers who found those anomalies, who identified those dual origin signals, who asked those uncomfortable questions. They did what the scientific method requires, but the institution did what self-preservation, not science, requires. It was a career massacre, silent, brutal, and perfectly documented. The researchers who spoke informally about these findings, and whose identities are known in the small world of high-energy physics, saw their professional situations change afterward, in ways consistent with having made institutional enemies. None can say it publicly. But the pattern of subsequent professional movement for multiple individuals, a move away from major collaborations and toward peripheral positions, was striking to anyone who follows the careers of once prominent physicists within these collaboration structures. They moved from their original institutions to smaller universities, far outside the main physics research circuit. One, once a leading figure in the Atlas collaboration, now publishes sporadically in unrelated fields. When asked about his time at CERN, he gives short, careful, non-committal answers. This kind of career trajectory, following these kinds of findings, tells a story even if the person does not tell it directly. But this was not the story of one person. It was a pattern. The careers of at least 4 leading researchers from at least 3 different countries were similarly derailed after they raised concerns about this anomalous data. This was not a first in history, but on this scale, at the heart of the world's largest scientific project, it was an earthquake. Science was eating its own children, because the truth was bigger than the institution could handle. But the evidence was not just coming from the inside, and this is what turned the story from an internal squabble into a global enigma. Another continent, a completely different experiment, a completely different team of physicists, and a completely different particle, but the same disturbing result. In April 2021, when the results of the muon G2 experiment at Fermilab in the US were published, the physics world held its breath. This experiment was measuring the anomalous magnetic moment of a particle called a muon, a cousin of the electron about 200 times heavier, with the highest precision in history. The Standard Model's prediction for this value is one of the most precise calculations in physics. And what the experiment found was a discrepancy. The measured value was different from the predicted value by a statistically significant 4.2 sigma. What does this mean? 5 sigma is the gold standard for a discovery. 4.2 sigma means something is horribly wrong, and it's not a coincidence. It's as unlikely as a stadium full of people flipping a coin 100 times and all getting heads. But that wasn't the most epic part. The most epic part was that this result confirmed the results of a completely different experiment done 20 years earlier at Brookhaven National Laboratory. Different facilities, different teams, different experimental setups, 20 years apart, but the same deviation in the result. This made a systematic error impossible. The deviation was a property of the muon itself, or rather, a property of the quantum vacuum in which the muon swims. Something was participating in those vacuum interactions, and there was no place for it in the Standard Model. And the most incredible part, a theoretical calculation using the wave-echo framework showed that the magnitude of these perturbations fell within the range of the measured discrepancy. It was a coincidence of magnitude. But, in physics, coincidences of magnitude between independent experiments are where serious investigations begin. This was no longer just a problem for CERN, this was a problem for physics itself. And the problems grew bigger, because this wasn't just a problem with tiny particles, it was a problem with the existence of the entire universe. The matter-antimatter asymmetry, one of the deepest, most fundamental, most stubborn mysteries in physics. According to the Standard Model, for every particle, an antiparticle was created in the Big Bang, in equal amounts. But if that were the case, they would have instantly annihilated each other, and the universe would be an empty soup of radiation. But we are here. Stars, planets, life exist. This means that symmetry was decisively broken in favor of matter. We have measured this breaking, which we call CP violation. But there's a problem, a huge problem. The amount of CP violation we measure in the standard model is orders of magnitude, but orders of magnitude below what is needed to explain the matter dominance we observe in the universe. This is one of the most important open questions, and there is a solution developed by credentialed researchers, published in reputable physics journals, the CPT symmetric universe or mirror universe model. According to this model, our universe and its antimatter counterpart were created simultaneously at the Big Bang. One became matter-dominant, the other antimatter dominant, and this model makes specific, testable predictions about neutrino oscillations. But it also makes a more shocking prediction. If this mirror universe exists and is adjacent to ours at the level of the quantum vacuum, then extreme energy events that stress the vacuum boundary will produce detectable artifacts from that mirror universe. And what would those artifacts look like in the detectors? Structured anomalies with dual origin characteristics, carrying information from a universe where the standard model parameters are slightly different from ours. Exactly. The very thing found, reclassified, and locked away at CERN. This was no longer a coincidence. This was the intersection of evidence from three completely different paths: an internal scandal, an independent external verification, and a theoretical framework that could explain the existence of the entire universe. They were all saying the same thing: beauty and hope. Because those anomalous signals recorded at CERN, those wave echoes, if they are real, are the first whispers that that wall may not be entirely insurmountable. They are like a message from a neighbouring shore, whose meaning we cannot decipher, but whose existence we know. You may never be able to speak with those other yous, but the possibility of feeling an echo, a shadow of their existence, even with our most advanced machines, breaks that absolute loneliness, even if just a little. It is a sign that the universe may not be so cold and indifferent after all. And you are a part of this lonely crowd. When you look back at your life, you think about those big what-ifs. What if I had done this differently? According to this theory, those what-ifs became the reality of another you, somewhere else. Your life is a chosen path. But all other paths are also being walked by someone. This gives your choices a weight and meaning they never had before. You are not just the hero of your own story. You are the sole and unique representative of this branch in an infinite network of stories. We are both creator and victim, both personal and cosmic, both alone and together in an infinite crowd. These paradoxes are where modern science has brought us. But beyond these personal reflections and philosophical vertigo lies a more concrete, more urgent, and perhaps more moral question. If these leaks, these echoes are real, what should we, as a species, do with this knowledge? Because this is not just a question about what we are, this is a question about what we should be. And the answer to that question transcends the boundaries of science and enters the realm of ethics. And this ethical question confronts us with our fourth and perhaps most painful paradox, the deep chasm between the act of knowing and the refusal to know. On one hand, we have one of the greatest scientific endeavors in human history, a machine costing over $9 billion, built by tens of thousands of scientists and engineers from over 100 countries over more than a decade. It has one purpose: to know, to understand the most fundamental secrets of the universe, the smallest building blocks of matter, the first moments of existence. This is the most magnificent monument to our species' unwavering belief in, curiosity for, and dedication to knowledge. But, on the other hand, there is the attitude of the same institution, the same scientists. When that knowledge becomes uncomfortable, their reaction when faced with those dual origin signals, that structured background, when knowledge itself becomes a threat to the system's self-preservation reflex kicks in, and that reflex is to refuse to know. Therefore, our most advanced tool for gathering knowledge also becomes our most sophisticated mechanism for producing ignorance. How can we strive so hard to know, while being so afraid of what we find and choosing to ignore it? The most tragic part of this situation is the betrayal of the spirit of science. Science is the courage to face uncomfortable truths. Science is being ready to kill your favorite theory with a single ugly piece of data. But what is happening here is the exact opposite. When an anomaly is found, instead of investigating it, we reclassify it. When a question is asked, instead of answering it, we silence the one who asks. This is the bankruptcy of the self-correcting mechanism of science. Because when you test a hypothesis and find it to be false, you gain knowledge. But when you refuse to test a hypothesis, you are simply choosing ignorance. Those archived data, that unexplained instrumental artifact, label, are not scientific conclusions, but monuments to intellectual cowardice. This is sad, because it shows that humanity's greatest intellectual adventure can succumb to the self-preservation instincts of an ordinary bureaucracy. But even this situation has a beautiful side that shows the resilience of the human spirit. Because, as the institution fell silent, individuals began to whisper. Those rejected researchers, those leaked lecture notes, those discussions in closed forums. These are proof that the hunger for truth can overcome institutional walls. Knowledge is like water. No matter how much you try to block it, it eventually finds a crack and leaks through. The persistence of that handful of people in seeking the truth may be stronger than the institutional inertia of a massive collaboration of thousands. And you are in this paradox too. How many times in your life have you chosen to ignore an uncomfortable truth? How many times have you taken refuge in a comfortable lie rather than a difficult truth? We all do it, because knowing brings responsibility, and sometimes that responsibility is too heavy. What is happening at CERN is a massive example of how this very human weakness can manifest even in the most high-tech environment. This brings us to the fifth paradox, the mind-boggling mismatch between the scale of the action and the scale of the consequence. On one hand, there is the action that takes place. Two protons, two particles too small to be seen, too light to be imagined. They collide for less than a billionth of a second inside a 27-kilometer tunnel, hundreds of meters underground. This is one of the smallest, most isolated, most controlled events in the universe. But, on the other hand, if these theories are correct, there is the potential consequence of that microscopic action, the change in the shared reality perception of all humanity, the unwitting rearrangement of memories that exist in the minds of 8 billion people, the silent, unnoticed rewriting of shared history. How can such a small action lead to such a massive consequence? How can the dance of two protons affect the memory of an entire species? There is a tragic and frightening aspect to this thought, because this is a kind of cosmic injustice. Only a handful of physicists and engineers decide what happens in that tunnel. But the consequences, if any, affect all of humanity. This is the greatest example of taxation without representation in history. No one asked us. No one got our consent. No one asked, would it be a problem if we stressed the fabric of reality a little? We think we have a say in our own destiny, but we may actually be a massive side effect of the scientific curiosity of a very small group. This is the feeling of completely losing control in one's own universe. But this incredible connection also has a deeply hopeful side, because it shows that the universe is not made of disconnected, isolated parts. It proves that everything, from the smallest to the largest, from the most abstract to the most personal, is connected by invisible threads. If the collision of a proton can affect your memory, it means you are a part of the universe, not a separate being observing it, but a being that breathes with it, vibrates with it. This is a feeling of wholeness at the deepest level. It is one thing to say we are stardust. It is another thing entirely to say that a fusion reaction in the heart of a star could, billions of years later, shape a memory of yours. You are in this connection too. Every step you take, every word you say, every choice you make, no matter how small, creates a vibration in this vast network. Your actions too, perhaps in ways you never imagined, have consequences for people you've never met. What is happening at CERN is the most extreme, most mind-boggling example of this principle. Thus, we behold this philosophical landscape where the desire to know leads to ignorance, where the smallest action has the greatest consequence, where we stand at the gate of a hell and a heaven of our own making. These paradoxes are as enlightening as they are disturbing. They reflect the most fundamental tensions of the human condition on the grandest stage of the universe. But, after all these thoughts, all these reflections, one question remains, a more personal, more internal question. After hearing all these possibilities, after hearing these whispers echoing in the dark corridors of CERN, what do you feel? When you are confronted with the idea that reality itself, that ground you thought was most solid, might actually be a thin membrane, and might even be leaking, what awakens within you? On one hand, there might be the awe and wonder brought by these discoveries, the excitement of seeing how strange, how wonderful, how unexpected the universe is. But, on the other hand, there might be a deep anxiety and fear, the cold shiver created by the feeling that control has been lost, that everything we know could be turned upside down, and that no one is at the wheel. Awe or fear, curiosity or anxiety, whichever you feel, you are not alone. And perhaps the right answer is to feel both at the same time. Because this is precisely what it means to be human. To be both brave enough to reach for the stars and vulnerable enough to be afraid of the dark. Creator and victim, personal and cosmic, alone and together, knowledge and ignorance, action and consequence. These contrasts summarize the landscape we have reached at this point in our journey. We now know that this story is not just about particles and data. This story is about us. It is about our curiosity, our hubris, our fears, and our hopes. But, beyond these philosophical reflections, there is one more question to be answered, perhaps the most important one. If these leaks are real, if these subtle interactions between realities are happening, is this just a past event? Or does it point to an ongoing, accumulating, and perhaps irreversible process? Because CERN may not have just recorded something that happened, it may have done something else. And the nature of that action takes us to the next, an even deeper layer of this story. And therefore, we now face a deeper question. If CERN did not just record something, but did something else, what is the nature of that action? This brings us to the final, most intimate layer at the intersection of physics and philosophy. We are no longer asking what the machine found or what it did. We are now asking what our existence itself means in the light of this knowledge. Because, if that membrane between realities is thin, if our memories carry the whispers of cosmic events, then we must reconsider our most fundamental assumptions about the nature of being human. This is where the story is not just about science, but about the soul. At the center of this spiritual inquiry lies our sixth paradox, the tension between absolute silence and meaningful noise. On one hand, we have one of the loudest machines in human history, a machine deep underground, smashing billions of protons per second, mimicking the birth cry of the universe. And in that noise, our detectors, the most sensitive ears in history, are searching for something meaningful, a signal, a pattern, a whisper. But, on the other hand, there is what emerges when that whisper is found, an absolute institutional silence. Reports are reclassified, researchers are silenced, data requests go unanswered. We built the greatest microphone in history, and when we didn't like what we heard, we turned it off. How can we strive so hard to find meaning in the noise, only to draw an even greater curtain of silence to suppress it when we find it? There is a tragic truth to this, because it shows that we are not seeking truth, but only the version of truth that gives us comfort. When we cannot transform the meaningful noise, that structured background or dual origin signals, into a manageable story, we find solace in labeling it as meaningless noise, as an accept, instrumental error. This is not intellectual laziness, but an existential fear. We prefer to pretend there is no reality at all rather than confront a reality we cannot understand. This silence is not a show of strength, but an admission of weakness. And the saddest part of this silence is that it deprives us of the real story, of what that meaningful noise is trying to tell us. But even in this silence, there is a beautiful, hopeful truth, because that noise, that signal, does not go away. It is stored in the archives. It is stored in the notes of that lecture that silenced the room. It is stored in the minds of the scientists whose careers were derailed. There is an irrepressible persistence in the nature of truth. No matter how deafening the silence, a whisper at the right frequency will eventually resonate and be heard. Institutions may choose to forget, but the data remembers. And you are in the middle of this paradox too. In your own life, what are you striving to hear, and what are you drowning in silence to avoid hearing? That intuitive whisper inside you, that something isn't right feeling, is it meaningful noise or just random anxiety? We are all trying to find a balance between the noise of the outside world and the silence of our inner world. But what if the most important message is hidden right at the intersection of these two? This brings us to our seventh paradox, the mind-boggling contradiction between recording everything and actively forgetting. The detectors at CERN are the most perfect memory machines humanity has ever created. The Atlas detector processes about 1 petabyte of data per second. That's enough information to fill more than 200,000 DVDs every second. Nothing escapes. Every collision, every track, every energy deposit is recorded with extraordinary precision. We are the most meticulous archivists in history, but we are also the most selective amnesiacs in history. When we find that 3% anomaly in that vast sea of data, the one that doesn't fit our story, that makes us uncomfortable, what do? Do we set up a research institute to understand it? No. We stick a label on it and put it in a digital attic. We are a species with the power to remember everything, yet we choose to actively forget. There is a tragic aspect to this situation, because this is not innocent forgetfulness. This is a conscious act. This is an act of evidence tampering. It is an attempt to prevent future generations from examining this data and drawing their own conclusions. This is a betrayal of our own scientific heritage. It is like building a perfect library and then labeling the most important books dangerous to read and locking them in the basement. This is sad, because it means we are not just locking away a data set, but a potential future, a whole new way of understanding. But even this active forgetting has a paradoxically hopeful and beautiful side, because those books in the locked basement are still there. They have not disappeared. They are just waiting for the right person with the right key, someone brave or reckless enough to open that door. The memory of institutions may be short, but the memory of data is eternal. The act of forgetting does not erase the record itself. It only makes it harder to access. This gives an unshakable faith that the truth will eventually come out. Maybe not today, maybe not tomorrow, but one day, someone will enter that archive and tear off that unexplained artifact label. And you, in your life, are constantly going back and forth between recording and forgetting. Your phone is filled with thousands of photos, a perfect record of your life. But how many do you go back and look at? Which memories do you highlight? And which do you bury in the depths of your mind? Is not your personal history also a collage of selected memories and actively forgotten truths? CERN's archive is perhaps just a massive reflection of our collective mind. And finally, we face the eighth paradox, the thin line between the fleeting nature of the moment and the permanent effect of accumulation. Each collision at CERN is a momentary event, a moment trillions of times shorter than the blink of an eye. The proton beams circle that 27-kilometer ring, 11,245 times per second. Collisions occur every 25 nanoseconds. These moments come and go, alone. They are almost meaningless. But if the wave echo theory is correct, the effect created by these momentary events accumulates. It is not like a sudden flood, but like the invisible micro cracks that slowly form in the wall of a dam. Each collision delivers another tiny blow to that wall. A single blow is not noticed. Millions are not noticed either. But after billions and trillions of blows, one day those cracks merge and the integrity of the dam is compromised. We can measure those individual collisions. But do we have a tool to measure that cumulative effect, that slow drift? There is a tragic and almost imperceptible danger in this situation, because we are beings evolved to react to sudden and dramatic dangers. We react instantly to a predator's attack, a fire, an earthquake. But we are blind to slow, cumulative, almost imperceptible threats. Like global warming, like plastic pollution, this potential reality drift is a problem where each individual moment seems innocent, but their sum can be catastrophic. We can say everything is fine after each 25 nanosecond collision, but after a decade of trillions of collisions, the meaning of the word fine may have changed without our knowledge. But we must not forget that this concept of accumulation also holds a deep and beautiful truth about life itself. Nothing is just a single moment. A character is formed not by a single act, but by the accumulation of thousands of small choices. A relationship is built not with a single grand gesture, but with countless small moments of kindness. Life itself is a cumulative sum of these momentary experiences, memories, and decisions. What is happening at CERN is perhaps just a reflection of this universal principle at the most fundamental physical level. Every moment matters, because every moment shapes the next, and you are a result of this accumulation. You are a cumulative sum of every moment you have lived, from the breakfast you had yesterday, to the book you read 10 years ago, to the heartbreak you felt 20 years ago. And every small choice you make today, every word you say, every step you take, adds another brick to that accumulation that is building the you of tomorrow. Your life, just like that data set in the collider, is a permanent record of momentary events. Silence and noise, recording and forgetting, moment and accumulation. These deeper paradoxes confront us not just with who we are, but with our relationship to time and knowledge. They show that the story at CERN is not just a physics experiment, but a meditation on what it means to be human. But, after all these thoughts, one final question remains. If these interactions are real and accumulating, is this just a one-way leak? Or could it be the beginning of a dialogue? Is it possible for our reality to leak into a neighboring reality? And if so, how are the us in that neighboring reality experiencing the whispers of our existence? And this question, the question of whether a dialogue has begun, brings us to the final and most dizzying layer of this philosophical journey. Because if this interaction is two-way, this is no longer a situation about us just observing the universe. It means the universe is also observing us, or rather, that another version of the universe is interacting with us, just as we are interacting with it. This is where the story ceases to be just a discovery log and becomes a potential first contact story. But this contact is not with an alien civilization, but with another version of ourselves. At the heart of this potential dialogue lies our ninth and perhaps strangest paradox, the imperceptible tension between a stable reality and a slow drift. On one hand, there is the solid and reliable world we wake up to every day. The hardness of the table you touch, the unchanging nature of the street you walk on, the certainty of your memories from last night. We build our lives on this assumption of stability. Reality is a fixed stage, and we are the actors on it. But, on the other hand, there is the disturbing possibility implied by all the evidence we have examined in this documentary. Reality may not be a fixed stage, but a very slowly moving river, and we are the unwitting swimmers in that river. Each high-energy run at CERN might be changing the river's current by an amount so small that no one can notice. This is not a sudden change. This is a cumulative drift. Each time, reality itself may not be returning to its original configuration exactly. There is a tragic truth to this situation, because it may mean that we are slowly losing our home, but we are not even aware of it. Just as a coastline erodes millimeter by millimeter with each wave, our reality may be eroding with each collision, in a way we cannot measure. This is a loss we cannot mourn, because we cannot know exactly what we have lost. All that remains is that vague, unnameable feeling that something is not as it used to be. It is to be a refugee of one's own past and world, but this drift might also hold a magnificent, beautiful truth about the nature of the universe. It shows that reality is not a dead object, but a living, breathing, evolving organism. It is reacting to our actions. It is responding to our experiments, our curiosity. This elevates us from being passive tenants of the universe to active partners evolving with it. The universe is in a dialogue with us, and this dialogue is slowly changing its nature. And you are in this river too. You assume your life is stable and predictable, but what if all this certainty is just an illusion caused by the slowness of the current? This possibility turns every normal moment, every ordinary day into something priceless. Because that moment is an instantaneous photograph of a reality that may never be exactly the same again. This brings us to our 10th paradox, the bitter irony between the illusion of control and the reality of accident. On one hand, there is CERN, the pinnacle of human intentionality and control. Every magnet, every cable, every line of software has been planned and implemented with absolute precision by tens of thousands of people over more than a decade. The goal is clear: to test the standard model and find the physics beyond it. This is the most controlled, most deliberate scientific act in history. But, on the other hand, there are all these anomalies at the heart of this story. Dual origin signals, Mandela Effect correlations, unexpected peaks. None of these were planned. None of these were intended. They are the side effects, the accidents of that perfect plan, that flawless control. How can our greatest act of control lead to our greatest loss of control? How can our intention to know everything bring us face to face with the greatest unknown? There is a tragic aspect to this, because this is humanity becoming a victim of its own intelligence. This is a modern version of the Tower of Babel. We built a tower so high to reach heaven, that is absolute knowledge, that the tower itself, under its own weight, began to collapse in unexpected ways. While trying to become masters of nature, we may have actually only proven how little we know and how little we can control. This is the deep sadness created by the possibility that our greatest success could be our greatest failure. But we must not forget that this accident also reveals a very beautiful truth about science and life itself, because the greatest discoveries are often not planned. They are found by accident. Penicillin, X-rays, the cosmic microwave background radiation, all were things found by chance while looking for something else. This shows that the universe is always bigger, more creative, and more surprising than our plans. It is a humble reminder that the most valuable knowledge may be hidden not in the answers we seek, but in the questions we never even thought to ask. And you, in your life, are constantly living this dialectic. You plan your life, your career, your relationships, what you will do tomorrow, but are not the most transformative moments of your life. Often those moments of accident when your plans are completely upended, that unexpected encounter, that sudden inspiration, that tragic loss. Your life too is a poem written between your intentions and the accidents of the universe. And perhaps the most beautiful verses are always the unexpected ones. Finally, we face our 11th and final paradox in this journey, the creative tension between the absence of meaning and the act of creating meaning. At the end of this story, we have no definitive answer. Are the wave echoes real? Are we in a simulation? Are we talking to a mirror universe? We don't know, and maybe we never will know for sure. The universe may remain indifferent and silent to these deepest questions of ours. This may mean that meaning is not inherent in the universe, but is something that must be created by us. This is a sense of cosmic emptiness, the possibility of being lonely beings searching for meaning in a meaningless universe. But I think this situation reveals the most powerful and most beautiful truth of being human. Meaning is not something to be found, but something to be created. Those dual origin signals themselves may be meaningless, but those scientists who take those signals and build theories upon them, write papers, give lectures, and even risk their careers, have given meaning to that meaningless noise. The Mandela Effect, on its own, may be a meaningless psychological quirk, but those researchers who tried to connect it with CERN data tried to create a pattern, a story, a meaning from those disconnected dots. And you, every day, are doing exactly that. Life itself may be inherently meaningless. It is just a random dance of atoms, but you give meaning to that dance. You fall in love, you make art, you work for a cause, you teach a child something. You are a being who rebels against a meaningless universe with the act of creating meaning. And this is perhaps the most heroic thing we can do. Creator and victim, personal and cosmic, alone and together, knowledge and ignorance, action and consequence, silence and noise, recording and forgetting, moment and accumulation, stability and drift, control and accident, meaninglessness and meaning. In our long philosophical journey, we have revolved around these paradoxes. They have shown that this story is not just about CERN, it is about us. They were a reflection of the human condition. And now, as we approach the end of this intellectual journey, it is time to bring all these pieces together. We now know that this is not just a science story. This is a moral story. This is an existential story. And now, armed with all these thoughts, we must return to the starting point, to that machine, to that data, and to that one, big, unanswered, and refused to be answered question. In this video, we examined CERN's mysterious data and the possibility of inter-reality leakage. But I didn't tell you one thing. The silence of the universe actually hides the biggest paradox. Space is so vast that it should be teeming with intelligent life. But where are they? On our next journey, we will dive deep into the Fermi paradox. Why aren't the aliens contacting us? Are you ready?